Hi everyone, this is Troy Tacey from Fordham University, and this is part 4 of my series of short videos to help us understand what's happening with the coronavirus epidemic. What this fourth video is going to be about is we've probably all heard the term flattening the curve in the last couple weeks or so. And what we're actually going to talk about today is flattening of two curves and how social distancing allows us to do that. So we're going to be able to talk a little bit about what's been in the news and what you've read in the press and whatnot recently. And we're also going to think about a proper way to look at the data that keeps coming in about the new cases both in the US and around the world. So what I want us to think about real briefly here is this idea of social distancing and why we need social distancing. And to some degree the answer is that when we look at something like an epidemic, we can think about the biology and we can also think about the social science. So if we go back to our idea of the initial reproduction number, remember that we find that reproduction number by looking at the number of contacts multiplied by the transmission rate multiplied by the duration of the infection. Now, two of these things, there's not much that we can do anything about. So the transmission rate, we can perhaps wash our hands more often, more frequently, but someone sneezes on us, the biology tells us whether or not we're going to get sick. Similar for the duration of the epidemic. These are things that we can't do a lot about or can't significantly change, at least in the short term. Biology tends to be a long-term solution, right? So we can develop a vaccine, but that is perhaps a year to a year and a half out. So we can't change the biology in the short term, but what we can change is the social science. So the other important element that's in this reproduction number is the contact rate. We can do something about that now through this idea of social distancing. So when we interact with fewer people, we lower that reproduction number and we are able to stop the spread of at least some spread of this infectious disease. So what I want to do briefly is let's jump back into our Excel spreadsheet and we can talk about this idea that we've seen in the news of flattening the curve, right? So if we social distance, we lower this parameter C and we take what could be potentially a big epidemic and we make it at least somewhat smaller when we incorporate social distancing, right? So when we incorporate social distancing by lowering C, we're both lowering the peak of the epidemic, and the other thing that we're doing is we're pushing that peak of the epidemic out farther into the future. So again, if we go back to the original epidemic that's large and has an early onset, then if we move to a different lower parameter for C, then that peak is lower and the epidemic happens later in the future, so we have more time to prepare. And again, I'm sure many of you have seen a graph like this already somewhere in the news or other places. But the idea here that we're really concerned about is that this bottom grid line, let's imagine that that's the healthcare capacity of, say, the United States. If the peak of this epidemic is above our healthcare capacity, then that's going to cause, of course, very, very large problems. So the first flattening of the curve that has already been talked about quite a bit, and I won't spend much time on, is that if we incorporate social distancing, we lower the reproduction number, then we can perhaps push that peak of the epidemic to a level that is within the capacity of our current healthcare system. So that is, that's the first curve that we're going to flatten. The second thing that I want us to do is think about how we look at data from this epidemic. And then what I want us to do is see what that tells us about how effective social distancing is. So the first thing that I want us to do is let's jump over very briefly to a website called worldometers.info, and it has a whole bunch of data on lots of different things. So world population, society and media, the environment, food, a whole bunch of different stuff. And one of the things that it has a special section on right now is the coronavirus epidemic. And if you go to this section, you can look at the world, you can look at individual countries, you can look at individual states, you can look at lots of different stuff. So let's look at Italy briefly. So we know that over the past about 3.5 weeks, Italy has been incorporating harsher and harsher requirements that increase social distance, right? So beginning in the third week of February, all the way through the last few days, Italy has been creating harsher and harsher standards for social isolation. And if we look at the total cases of coronavirus in Italy, it still looks like a pretty scary picture. We're still seeing the standard exponential increase in cases, and that perhaps could be worrisome to us, that maybe social distancing isn't actually doing very much. In reality, it is, and I'm going to show you in a moment how we know that social distancing is doing good things in Italy. But the first thing we need to do is figure out how we look at the data of an epidemic in the right way. So if we just look at those cumulative infections that we have over here, as we see in Italy, we're looking at an exponential curve. And our eye as human beings isn't very good at recognizing differences in exponential increases. But one thing that we're very good at doing is recognizing a change in a linear relationship. So what we should be doing when we look at this data is not looking at cumulative infections, but instead we should be looking at the log of the cumulative infections. And when we do that, what we get is, because these cumulative infections follow an exponential curve, if we take the log of it, then what we get is a straight line, at least for part of the epidemic. And I'll explain what part in a moment or two. But if you think back, and you probably learned this at one point in either a high school math class or a early college math class, when you looked at logarithmic and exponential functions, if you take the log of an exponential function, you get a line. So what happens then if we look at this data in terms of a log function? Okay, so cumulative infections, as we just said, at least for part of this epidemic, follow a linear relationship. Now, if we plot this relative to the total infections in the epidemic, let me just reorganize this slightly. What we see is that the linear part of this log curve holds until we get to about period 65 or so, right? So it stops being linear when we hit right around this point. When does that happen on our epidemic curve of infections? Well, all the way through this portion of the curve, we're seeing cases increase at an exponential level, and then we flip from having a convex curve to having a concave curve. When that flip happens, that's exactly where we lose that linear relationship in our log of the cumulative infections. So when this curve breaks off and it drops below my ruler here, we know that we're pretty close to the peak of the epidemic, because we're in that portion of this curve that flips from being convex to being concave, and then again it doesn't have a linear relationship because we're falling off the other side of these infections. Okay? Now, if we go to the US data and do the same peek at the data here, again, this is the Worldometer's information. These are the total coronavirus cases in the US. Again, if we look at just the total cases, we see this exponential increase. But if we flip and we look at these total cases on a logarithmic scale, once the epidemic set in, 2 or 3 weeks ago, the epidemic is following a very nice linear relationship here. So we're seeing that the cases in the US fall right along that line because we're seeing that exponential increase, and when we viewed from a logarithmic scale, everything falls in line very, very nicely. Now let's go back to the model that we had up on our spreadsheet. And again, I'm going to put the cumulative infections in the center. And again, I'm going to change this contact parameter that is sort of a proxy for social distancing. What happens is something that is very clear. So if I go from a parameter of 0.5 to a parameter that is 0.4, what you notice is this blue line, we keep that linear relationship over period about 10 to period 65, but this curve becomes much flatter. So again, parameter 0.5, it's a much steeper curve. Parameter 0.4, it's a much flatter curve. So we can see the change in this log of the cumulative infections much more easily than we can recognize a difference in a change in an exponential curve. Okay? Now, what we could do then is we could think about changing our social distancing somewhere along the process of this epidemic that we're seeing. Right? So let's suppose that the epidemic runs along for, say, 25 periods, and then at period 25 we shift from having a parameter of 0.5 to having a parameter of 0.4. Then what we would expect to see is that this log of cumulative infections graph should have a change in slope when we implement that social distancing. And if we go down to this curve, we can see exactly that in our model that we're playing around with. So initially, up to period 25, we have that expected linear relationship between period 10 and period 25. We implement social distancing in the Excel spreadsheet by lowering the contact rate. And what we see is a new linear relationship that follows that new social distancing measure. If we look at real data, we see exactly the same thing when we look at the data from Italy. So remember, when we looked at Italy by itself in terms of just the total number of cases, it doesn't look like much has changed. We're seeing a continual increase, exponential increase in the total number of cases. But if we look at Italy on a logarithmic scale, what we see is that as they've implemented social distancing, again beginning in late February through to present day, they've had harsher and harsher measures of social distancing. What we're seeing is every time they implement these harsher measures of social distancing and social isolation, this curve is getting flatter and flatter. So we've got approximately linear relationship here, but then our curve falls below the ruler. If we look for the next part of the slope, again, right, it sort of follows a linear relationship, but again, it's falling below the ruler. So we know that even though these cases are increasing exponentially, this social distancing is having an effect because this logarithmic scale is getting flatter and flatter. So what should we expect in the US now that we're beginning to implement this social distancing measures? Well, what we would expect to see if everything in the world was held constant is that this linear relationship that we see from about approximately the beginning of March through today, which is March 19th, although the data only goes through March 18th in this plot, it goes through yesterday, we would expect to see that this curve in the next week or so should get a little bit flatter as social distancing starts to play an effect. Now, in the US, there's a little bit of a problem, however, right? So we've been under-testing the number of people that have that could potentially have coronavirus. So one of the things that might complicate this analysis is that if we increase the level of testing, as we've done in the last few days, just because we're testing for more people, we might temporarily see an actual increase in this logarithmic scale in terms of the total number of cases. So we might see that this curve goes up just because we're testing more people, but then once it goes up, again, that social distancing should play out and give us a flatter curve than what we see with those increases in testing. So one thing that we can do to get around this change in the number of testing and still see that same relationship, perhaps moving forward in the data, is instead of looking at the total number of cases or the cumulative number of cases, we could move down and look at the total deaths, say in the United States. So again, this process is following this exponential relationship. If we plot it on a logarithmic scale, again, we see a pretty nicely fitted line here. Now, because deaths don't depend on how many people are tested, what we should see if social distancing is playing an effective role in slowing down the spread of the epidemic is a flattening of this curve of deaths. So we would expect if the slope is currently about this, if we wait a week or so and have 7 more data points, those next 7 data points, or maybe a little bit longer than that, we should see that this curve gets a little bit flatter. And that's a very easy way that we can look and see if social distancing is having an effect on the outcome of the spread of this epidemic. So in summary, what should we watch for over the next 2 weeks? Number one, if social distancing is effective, we should see this logarithmic measure of the number of deaths. That curve should get a little bit flatter. We can also watch the cumulative infections in that same website that I had up a moment ago. But again, the concern is that if we increase the amount of testing in the US, that curve could actually get steeper, looking at it in terms of the logarithmic scale. So probably watching the number of deaths is going to be a better indicator of whether or not social distancing has been effective or not. So that's something that you can watch for in the next week or two. The other thing that you can do a little bit longer term is, again, if we bring back the spreadsheet, remember that as long as the epidemic is still on this upswing, we're going to see this linear relationship in the log of the cumulative infections. We expect to see perhaps some flattening of that in terms of the effect of social distancing. But the other thing to watch for, if you're sort of wondering when the epidemic may be ending, is remember that when this curve goes from convex to concave, we're leaving that exponential section of the epidemic. So we're getting closer to the top when we begin to lose this linear relationship. So if we incorporate social distancing, we don't change anything for a while, and then we start to see this curve bend, and we no longer have a linear relationship. That's going to tell us that we're getting pretty close to the peak of this epidemic. So again, if nothing changes, we've got a line, we get close to the peak of that epidemic, and note that right around in here, we're losing that linear relationship. So we're starting to get a curve, and that curve is going to tell us that we're nearing or at the top of that epidemic in terms of, on top of that curve, in terms of the number of current infections. So those are some things that we can watch for over the next couple weeks to a month, something of that nature. Now, the next thing that I'm going to do in this series of videos is I'm going to think about a counterfactual. So we can think about the fact that if we have this linear relationship, and in terms of the logarithmic number of cases or logarithmic number of deaths, and we just let everything be, then the path that we're on, or the trajectory, should follow that line. And if we look at the distance between a projection of where that line would be today compared to where it was, the trajectory that it was on, say, 3 or 4 weeks ago in somewhere like Italy, then we can actually measure the effect of social distancing in terms of the number of reduced cases. So that's what we'll be looking at in our next video, is asking essentially a series of questions. What if Italy had not enacted these measures to socially distance everyone from everyone else? Where would we be today? And then I plan in a couple weeks, hopefully we can do the same thing with the US, because hopefully the social distancing measures that we're putting in place will also be effective, and it will also see an effect that we can measure within the data.